Good evening everyone. Our next topic in classical mechanics is supremacy of Lagrangian mechanics over Newtonian mechanics. Dear students, first of all, the title of this topic is quite unjustified because the comparison of these two mechanics is like comparing a landline telephone with a mobile phone. Both the devices are fulfilling the basic or the fundamental need of communication, but mobile phone of our present era is much more superior as well as sophisticated device as compared to the landline phones. But this topic or the title of this topic, my personal opinion is I just have a bit negative inclination of this title because Newton and Lagrange both are very few superfine mathematicians the world has ever produced, and these type of mathematicians, we can say, or it's my personal opinion, are born, cannot be trained, or we can say this class of mathematicians are very rare, or very handful of mathematicians are lying in this class, like Ramanujan, Euler, Laplace, Leibniz, Gauss. So these mathematicians are very superfine mathematician of the scientific history. So dear student, comparing these two mechanics, Newtonian as well as Lagrangian mechanics, is, I am not saying that one mechanics is superior than the another. We just can say when there was no mobile phone, telephone was a very excellent piece of scientific technology, and in this time or in our present era, mobile phone is also one of the sophisticated device. So for my personal opinion, I can say both mechanics are very excellent mechanics, but still we can compare these two mechanics. So just stating that supremacy of one mechanics over the another is very superfluous. So dear students, let's start our topic. Lagrangian mechanics and Newtonian mechanics. Both the mechanics are solving the problems, dynamical problems, very easily, very nicely and successfully. But still we incline more to Lagrangian dynamics or Lagrangian formalism because of its more applicability. It's because of its easiness, because of its comprehensiveness. Lagrangian mechanics is much easier, more comprehensive and more handy than Newtonian mechanics. So there are few points. The first point is, in Newtonian mechanics, the fundamental equation which we generally use is F equals ma. Sometimes I got confused about this formula. I don't think it's a law or this is a definition, and whenever I think about this formula, I never got the answer that is it a definition or a law, or it's the mechanism of nature. We can say our nature works in this way, and this is one of the basic formula of our nature. So dear student, F equals ma, and you know from your elementary physics classes that F is a vector quantity, A is a vector quantity, and this is not a single equation. It's actually a set of three equations, and while using vectors, it's quite cumbersome to deal with vectors. You know the components of the vectors, angles which the vectors are making in a certain direction. So F equals ma is bit complex, bit cumbersome to deal with some mechanics or mechanical or dynamical problems. On another hand, you know, when we deal with Lagrangian, which is t minus v, and dear student, you will be very much surprised. This t minus v is no any physical quantity. T is kinetic energy, v is potential energy, their sum is total mechanical energy, and we don't know what is t minus v. You can visualize kinetic energy very easily. Any object which is moving with respect to certain observer is said to possess some kinetic energy, and if it is moving under the effect of some conservative force, then there is some potential energies associated. But dear students, you can never visualize what is t minus v. You can visualize t plus v. Suppose you have a bow and arrow and you stretch it to any specific target. At every instant of time you can easily visualize what is t plus v, which is the total mechanical energy. But what is t minus v? It's not a physical quantity. It doesn't have any importance in our physics, but mathematically it has very potential importance. So why we say Lagrange is a very finest mathematician? Because how did he got this t minus v? You cannot derive this Lagrange equation, although we generally deduce Lagrange equation from Hamilton variational principle, and Hamilton was a scientist, mathematician which was very much impressed by Lagrange. So I don't know how this quantity came to the mind of Lagrange, and while solving any problem, it's the result of, we can say, thinking out of the box. Thinking t minus v is a revolutionary idea at that time. So here t, v as well as L, these three physical quantities are scalars. So dealing with scalar is very much easier than dealing with vector. So first comparison of the Lagrangian mechanics and Newtonian mechanics is that in Newtonian mechanics we use vector quantities, we have to deal with vector quantities, which is quite cumbersome, and in Lagrangian mechanics we are going to use scalar quantities, which are very easy to handle with. Now dear student, the second point of comparison is this equation is, I can say, coordinate sensitive, and this Lagrangian, or more precisely the Lagrange equation we generally use, this equation is coordinate insensitive. Means you can work in cylindrical coordinate, you can work in polar coordinate, you can work in Cartesian coordinate, you can work in any type of curvilinear coordinate. You will get the same result and the same Lagrange equation. But in case of Newtonian mechanics, if you change the coordinate system from, say, Cartesian coordinate to polar coordinate system, or say to cylindrical coordinate system, the whole equation will get changed. Of course, it means you will not even recognize the equation, the basic structure of equation will change, which is not the case in this Lagrangian formalism. And in third case, before discussing third case, let's come to one of my favorite example, a very beautiful piece of example in physics for me, a simple pendulum. whenever I didn't get any idea about any equation or any concept, then I move to this example. So in simple pendulum, suppose at this position you are wishing to apply Newtonian mechanics, then as you already aware with your previous elementary physics knowledge, that you have to consider the forces, then you have to consider some directions, okay, then the component of the forces or the tension, okay, you can change the direction to mutually perpendicular direction arbitrarily. So there will be some component of this tension along opposite to this mg or in this direction, then centripetal force, and before doing all that you have to draw a free body diagram, okay. In free body diagram again you are going to mark all the forces and their components. But in Lagrangian mechanics, while solving the same problem, there will be no any need of the concept of tension. So what is tension here? Tension according to Newtonian mechanics is a force which we have to consider while solving the problem, and according to Lagrangian mechanics, tension is a constrained force. And by introducing the idea of generalized coordinate, which is the heart of our Lagrangian equation, by considering the generalized coordinate, we get rid of this constraint force tension, and we didn't even think about it. We didn't have any need to think about the tension force in Lagrangian mechanics. So the point is, the unnecessary constrained forces are dealt by the notion of generalized coordinates. But in case of Newtonian mechanics, you cannot neglect the constraint force. So we get rid of all the constraint force in Lagrangian formalism, and the seemingly complicated problem becomes very easy, which I have already told you in the beginning of this lecture, that Lagrangian mechanics is much easier than Newtonian mechanics and much more handy than our Newtonian mechanics. There is also the next point is also about its easiness of Lagrangian mechanics. So what is easiness? There are certain problems which are not easy to solve by using Newtonian mechanics, like double pendulum. In the example of double pendulum, you have also solved this problem by using Lagrangian mechanics. So we have to consider theta 1, here theta 2, and if we solve this problem by using Newtonian mechanics, it is very cumbersome. It contains very cumbersome solution. But by using Lagrangian mechanics, our calculation reduced to almost 1/4 or 1/5 as compared to the Newtonian mechanics. So again, I say, in some complex problems, yeah, we can say Lagrangian mechanics solve much cumbersome problems very easily. My next point is, in Newtonian mechanics, there was stress on geometrical approach This is in Newtonian mechanics. Much stress on geometrical approach. Geometrical approach means in any dynamical problem, in any mechanical problem, your first task is to identify all the forces, then draw the free body diagram, then apply parallelogram law of extradition or triangle law of extradition. Means in each and every problem you have to dealt with the geometry, sine theta, cosine theta, their addition, their subtraction, and all this stuff was purely geometrical. But in case of Lagrangian mechanics, there is a more stress on analysis, or we can say analytic approach. Analytic. One of the masterpiece. Have you ever heard that classical mechanics sometimes called analytic mechanics? The word analytic mechanics came from a very great work of Lagrange, and Hamilton termed the analytic mechanics written by Lagrange as scientific poem. The work of Lagrange, its original name was Mécanique analytique. This is, I think, Italic or French word, and its English counterpart is analytical mechanics, and Hamilton referred to that book, or we can say paper, of Lagrange as scientific poem, and from that paper or book the word analytic mechanics comes, because Lagrange tried to solve the mechanical problem using calculus, or we can say more stress on calculus, and here more stress was on geometry. So this is also one of the aspect of Lagrangian mechanics which was not in Newtonian mechanics. Then Lagrangian mechanics is more comprehensive. Why we call it more comprehensive? Because by using Newtonian mechanics we can solve many problems like simple pendulum, simple harmonic oscillator, pulley problem, wedge problem, sliding blocks on frictionless or frictional surfaces. But Lagrangian formalism can also be applied to solve a variety of problems, including electromagnetic fields. It's totally different field from mechanics. Field properties of material particles, motion of a charged particle in electromagnetic field, which you might also have heard, and which is also must also be included in your syllabus. By using Lagrangian method, solve motion of a charged particle in electromagnetic field, and RL, LC, RC circuits, and coupled circuit also. Means suppose we have an LC circuit, this is an inductor, this is capacitor, and if this inductor is coupled with another inductors, which is a, you can say, very different problem from mechanics, we can also solve this type of problem by using Lagrangian mechanics. So we can say Lagrangian mechanics has more comprehensive field, and Lagrangian mechanics span more variety of problems which are not only included in classical mechanics but also in electromagnetism, in particle physics. Those problems are also be solved or dealt successfully with the use of Lagrangian mechanics. And last but not the least, or I would rather say it is one of the most important aspect of Lagrangian formalism is this formulation. This Lagrangian formulation gives us the basic idea of conservation of large. Why linear momentum is conserved? Why angular momentum is conserved in certain forces? Why the total energy is conserved? Actually, we say the law of conservation of energy, the law of conservation of linear momentum, the law of conservation of angular momentum. We consider these as large, these statements as large. But the basic of these laws resides in the symmetry of the Lagrangian. Means a well-established connection between symmetry and conservation laws can be easily understood by using Lagrangian formalism. So there is a very great connection, and there will be a special lecture over that, and it is also one of the most important topic of our classical mechanics. Symmetry and conservation law means why total energy is conserved, why linear momentum is conserved, and why angular momentum is conserved. Because Lagrangian is symmetrical under certain operations. If Lagrangian is not symmetrical under those observations, then there will be no any conservation law. So this is also, I said, one of the most important aspect of Lagrangian formalism, and that was not last, that was second last. And the last is, as you know, classical mechanics is our older version of physics, and there is also one of the recent version of physics we called modern physics or quantum mechanics or quantum physics. There are so many names. In quantum mechanics, for solving the problem, Lagrangian formalism plays a very, very important role. Means the same idea, the same concept of Lagrangian, which was in classical mechanics, is also applied in quantum physics or our modern mechanics. And one of the important aspect which I would like to share with you is that the notes of this lecture will be found in the description of this lecture. Thanks for watching the video.